doing some programming, or you get stumped, or you got problems, or how do you solve this thing? The logic behind setting up programs. He's the fellow you want to see. He's from Nepal, PhD, University of Texas, Dallas. Right? And actually a undergrad in physics, if I recall. He taught physics at one time. So anyway, welcome. Actually,
Thank you. Well, let me start with one incident. Although Darren has a lot of more experience than me, I joined University of Nevada a little earlier than him. So on the corridor, when I was walking one day, I saw in his door something that is very familiar to me. What I saw in his door was a mesh model of the wing of the aeroplane. And there were about, I would say, a typical 747 aircraft wing would have, guess it, how many triangles?
How many
Guess it.
triangles?
Yeah, to model it. Guess it.
123 billion?
Nah. Make a realistic guess. It will have about, even in a coarse, in a very coarse way, excluding the engine. You know, if you put engine, it will be more. Just the wing. It will have about 600,000. Okay.
Talking fine triangles,
And I was working in 1986 in Texas Instrument. No, 86 in Texas Instrument. I was writing my PhD dissertation on a project in pilotless aeroplane that Texas Instrument got a big contract from the Department of Defense, and I was working on routing there. And I had to initially work with a model of Volkswagen car to fit it, and in solid modeling and generating a mesh. And you know, a very coarse mesh for Volkswagen, and we actually got the official, the company Volkswagen had made a mesh for the car. And the number of triangle, just to throw it to the student, you know, very, very coarse, was 60,000. Okay. And there, for the first time, we were several students, you know. Texas Instrument has a plan annually to attract talented students from various universities. They fund about 100 students. They give all the money, they pay all the tuition, and they hire also. You know. So I was one of them there. And there we got the idea, what is programming in real life and what is programming in classroom. In classroom, we program with a data size of 50, 60, 100, 200, 300, or sometimes 500. And if we go 1,000, we say, wow. Now, if you go to the real life, we are faced with 500,000 triangles, 600,000 triangles, you know, in real life. And I could see that I have a friend who has a poster in the door that actually points towards the reality. So I stepped in his door and I said, Darren, are you talking serious about this thing? He said, yes, I do free flow on this scale of, you know, mesh. So that is how our common interest started actually. You know. I did not know anything about free flow. All I was doing was, from the programming point of view and from computational point of view, how to generate good quality mesh, you know, so that it can be used very effectively for solid modeling, you know, for rendering. Rendering means to put a flash on it, you know, for rendering in computer graphics, you know. And then here is a person who is doing the same thing for mesh generation, and we also do that a lot. So I started looking into his area, and then we started some collaborative work. And we did some implementation. One of our students, Ed Bowker, was working on it, and we found very fast algorithms, actually, to generate good quality mesh. Our student actually disappeared later on. He had some personal problem, but we could put that thing on the web and it was working very fast. So today, I'm going to talk a little bit about how good quality mesh can be generated so that the computation can be done near real time. Now the term near real time, you should understand it. Nobody can do it in real time. Nobody can do it. Even nature cannot do it. You know what is the meaning of real time? There is no time between what you do and what you get it. You know, what you ask and what you get it. So everything when you say it is near real time. So you want to, change the position of an aeroplane wing, and immediately you want to display it on the screen. You don't want to wait it. You follow what I'm saying? And Daryl was talking that, Lakshmi, I have a vision that one day we will digitize the whole Las Vegas Valley, and we'll make a virtual map related to Yucca Mountain and fluid flow and all those things. I said, Daryl, let us first do it a small scale, maybe a few millions. You are talking about billions of triangles in reality. And in fact, that has to be done. And recently, actually, he took me to, no, I didn't go with you, somebody else. I went to NASA to visit in California. And they were exactly doing what he was doing. That they were talking about that. So I talked with the program manager. Are you talking about billions of triangles? Yes. How do you do it? Well, that's what we are trying to do it, If you do not know how to do a billion, break it into small part, try to do each part, and eventually we'll do the billion. So, if we really want to see this world, if we want to model this world, we really need fast algorithm, not just to handle millions of triangles, but billions of triangles. Because we are not just talking about one wing of the aeroplane, or just one aeroplane. As Daryl said, he wants to digitize the whole Las Vegas Valley. And fast forward 2 years, 3 years after Daryl said about his dream of digitizing the whole of Las Vegas, Google comes with the Google Earth. Everybody use Google Earth? It looks very fascinating. Google Earth is like this. If you do not know it, let me tell you, you can go tonight and download it, patch in your program, and Google supplies it free. You can virtually navigate to your home in the street from Earth. And you can see the car parked in your car, in the car of your home, and probably it depends upon how quickly they update it. Probably it will be about 3 months. Whatever was 3 months back, Google will already take it and put it in the web page and you can do it. And a lot of the countries in the world actually protested Google. India protested that. If Google does this thing, and Pakistan will come and see their things in Delhi, they can use it, and indeed, actually. So I think there are some security issues, that's why Google will not do real time. Probably Uncle Sam's agency will be doing real time through the satellite image. But Google is doing that. And I asked one of my students who was working in Google, how actually they do it. Do you know what the Google does? They actually go and give to the agencies. They actually will take the map. They will take the video map while driving in this thing and then take it. So, getting the grid, getting the mesh, or getting the map from above is one thing. But getting the map as you drive is another thing. Because when you use MapQuest or Google Earth or Google Map to get a map direction, you don't see the real thing. You just see a drawing of the map, right? Now they are preparing a real thing. Means little more closer to reality, not exactly real. That when you drive it and you see in the screen, you actually see all the physical structure, map of the physical structure as you look forward, not looking from up, you know. So if you are driving in Strip, you will see Mandalay Bay in one side and, you know, MGM in another side, you know, and you can have more realistic picture. And all the servers throughout, wherever Google's have put, they put all these maps. And then when you go there, these digital maps will be loaded and you can do it. So what I'm trying to tell you here, in reality, the size of the data is so humongous, so large, that ordinary programming technique would not be enough to handle it. If you are trying to load a map that you want to use in the next 5 minutes, but you can load it only, your system will load it only after 1 hour, it is useless. Right? Do you follow what I'm saying? So if you get the answer, after you actually need it, it is useless. That is why fast algorithms for manipulating and generating mesh is indeed very much necessary. And there is a field in computer science called computational geometry. Many interesting results, many beautiful results have been formulated and documented, and still it is progressing at a very high speed. There are 5 or 6 journals devoted on computational geometry, 3 or 4 conferences every year, and in almost every established university, there are people working on it. And today I will give you a brief, look into what is happening in computational geometry, so that we can develop mesh, we can write program to develop good quality mesh, and the program will execute very fast. I'm talking about executing a million-size mesh in less than a second. I'm talking about in the present-day computer, how we can do that. Okay, let me start with 2 dimensions. And some of the technique I will explain, actually you can do it by hand, and if you have the wish and strong will, you can actually write the program. So let me start with what is triangulation. Well, you are given a set of point sites in 2D. 2D is a very simple example, but we have to understand the problem through a simple example. So let us first understand in 2D. Point sites in 2D. Connect them so that the points are the vertices of triangles, and everything inside, I have to use one technical word, but I will explain it. Inside the convex hull, I'll explain it. It's not a big deal. Convex hull of the point sites is are triangles. Perhaps 95% of the mesh generation code rely on triangulation, and a fast way of doing triangulation. So let me explain you. So let me have it. So this is a set of points. It will not there. Maybe the set of points would be on the map of Las Vegas, or would be on the map of the aeroplane wing, or something like that. Where you pick the nodes. But to make it look beautiful, I'm just showing you this kind of point. So what we want to do is, given set of points like this, we want to have, first we want to have something like a convex hull. There is a very beautiful metaphor to understand convex hull. This is the convex hull. Any triangulation algorithm, unless the domain is given, if the domain is given, it will not be convex. If the domain is not specified, then you have to go with the, if it is saying that it is on two dimensions, you have to start with a convex hull. You can think these points are the head of the nails. And if you take a rubber band and let it shrink, wherever the rubber band will be in equilibrium, that is the convex hull. This closed area, these angles will be always less than 180 degrees. And this is the convex. So first thing is this. Then after that, we want to somehow triangulate it. And it can be triangulated in a variety of ways. Maybe this is one. This is not the only one way of doing it. So the people who work on fluid flow, computer geometric modeling, rendering, they want to generate this thing very fast. So this is the problem you understand. You are given a set of points, and how do you pick up the set of points? That's a different lecture. But you are given a set of points, and you want to generate a triangulation. Now let me start first with a brute force approach. Brute force approach is easy to implement, but it will be very, very slow. It will be correct. Now we just don't need only a correct answer. We want to generate the correct answer very quick. As I told you, generating a correct answer late is useless. Imagine you are trying to write an algorithm to forecast weather for tomorrow, and it correctly forecasts the weather day after tomorrow for tomorrow, then it's useless, right? Same thing in next generation. If it is too slow, it may be useless. So let us try to understand how to do that. One way, straightforward way. I call it empty triangle test. Now you have to understand what is the meaning of solution space here. Solution space is, you are given say 100 points. How many triangles you can generate from 100 points? It is like there are 100 people. In how many ways 100 people can make themselves into 3 groups? Much more than 100, you see. And a little bit of thought will. How many of you understand this notation? N choose 3. Yeah, my daughter in grade 11, she is doing that in Greenway High School. So, this in how many ways you can choose 3 things from N. N choose 3. And if you want to brush up your high school math, it is N factorial divided by N minus 3 factorial times 3 factorial. Now, if you expand this one, do you know what would be its highest degree polynomial? Highest degree will be, highest degree if there are n points, n cube triangles could be there, you know. So if there are 10 points, 10 cube is how much? 1,000 triangles, right? So if there are million points, million cube triangles will be there. That is, solution space will be million cube. So out of those million cube, I have to choose the appropriate triangle so that the mesh looks good and triangulation looks very appropriate, so that computation error is reduced. This is the crux of the problem. Now, people have been working on generating mesh almost 50, 60, 100 years back. I don't know, but where, you know. I have seen paper like written in 1940s on mesh generation actually. So they used to, you know what they used to do? So, consider all n choose 3 triangles. For each triangle, so consider this step 1. For each triangle, for each candidate triangle, check if it is empty or not. If empty, put it in your solution.
You mean by empty, do you mean?
I'll explain. Put it in your solution. Yeah, I could see that you are getting interested. You know? Put it into your solution. So, what is empty triangle? So these are the things. So my candidate, I choose my candidate triangle. Because programmer, see, in a program inside the code, it does not know, so you can choose any two, any 3 vertex. You know? So probably it will choose this one, and maybe it will choose this one, and maybe it will choose this one. Then what happens is, oops, it's not empty. It has got node inside it. Do you follow what I'm saying? So this is not an empty triangle. So it will check this candidate triangle and it will say, no, I don't want it. So it will reject it. Do you follow what I'm saying? Now, if you check this one and this one, and this is empty, I say, okay, it is fine. It will take it. Do you follow what I'm saying? So a brute force way, which is a correct way, I'm not saying that brute force way is a wrong way. Very correct way. Actually, you should always start with the brute force way, because then you understand the scope of the problem, and you understand, you get the deeper insight into it. Getting insight is very important. So, throw, accept. Even the commercially available code, about 1960s or something like that, they did similar thing actually. Not now. Otherwise they will go out of business and they do this now. But in the class we have to teach it that. It's the first thing to learn it. So, you do like this, it's very simple to implement. If you write a Fortran code, of course, then you will ask me, how do you determine whether a point is inside a triangle or not? If I have time, I will explain you. It's a very small routine, small function I can explain you, but let's not go in that detail because I want to give you an overview of the approaches. That's what they're for me. Give them the overview of approaches so that in the future, if they want to become a programmer to do this, they know how to do it. Or you want to develop a good code or you do research with it around, then you have to understand that. So, did you understand? You pick a candidate, throw the candidate out or accept the candidate in, right? Now, if you do for all possible n choose three candidates, and apply this rule of throwing and accepting, whatever you accept, you know what that is the next. Yeah.
What about cases where there's like, in the triangle that you accepted, there's 4 points in that region? There's actually 4 different triangles, because you could cut it this way.
No.
This way.
Once you have a selection, yeah, very good point. When you have a solution set, the next solution should not contradict with the existing solution. Yeah, he has a very good point. What he's saying like this, probably you have to say like this. See, you are coming to the point. I like that. Both are empty, right? That's what you are saying. See, this is also empty, this is also empty, right? Do you take it? No. Because this triangle and this triangle are contradicting. I'm giving an overview. So when you add to the solution, it should not contradict with the thing that was already there. That is intersection of 2 triangles. It's a very small test, another one. But let's not go in detail. But I like that, that you are understanding what I'm saying actually. So once you do this, you get a triangulation. So now let us pause for a while and how much it takes it. Actually, I still remember one of the associate of who was working as a postdoc with Terrell, Eaton Chen. Actually, he came one day and then he saw our code, which actually I had done his algorithm. I had implemented by using our data structure. On his book, he had a book on. Actually, it was isothermal, for heat flow actually. And Eaton was so surprised to see that it just runs like that, And I said, look, this is what computational geometry comes. The key is the solution space you consider should not be very large. The solution space you are considering should be very small. You follow what I'm saying? And here the solution space is very large. You are considering all possible triangles, the candidate triangles. You should consider only very few candidate triangles in which you are going to get the solution. Okay, so this thing, you got the brute force way, right? Okay. Now I will slightly give you a very smart way of doing it, which is being done at present by all commercial next generation softwares. And this is called Delaunay triangulation. Smart way. Use the concept of Delaunay triangulation. Now, Delaunay triangulation is such a fertile concept. Its history is about 150 years old. Even Gauss did it. The scientist Gauss from Germany? Even Gauss did it. If you ever go to Germany, I think they stopped issuing mark, but when they had a mark, 10 mark note had a triangulation of map of Germany, and the algorithm to generate the triangulation was Gauss, and a picture of Gauss was there. So that tells you that how important triangulation is, and how important, if Gauss was attracted to triangulation, it is not a small thing. Now Delaunay he did not develop the first algorithm in terms of this thing, but he characterized the triangulation. See, characterizing is one thing, computing is another thing. So Delaunay characterized triangulation about 100 years later. what he did is, and this is called empty circle of Z. This is a wonder algorithm. Conceptually, it is so simple. I will give you, all of you will be able to do it actually. I have got set of points. Of course, in 3 dimensions it will be much harder, but there are Delaunay tetrahedron in 3 dimensions, we will not go there. And you know what? It captures convection automatically without even saying it. That is the beauty of Delaunay triangulation. Okay, so I want to do Delaunay triangulation. So, rule. If you can draw an empty circle passing through 2 point sites or nodes, whatever, 2 nodes, point sites or nodes, 2 point sites, V connected. Okay, let me do that here. Look how surprising it is. Let me see. I'm not very good in drawing circles, but you can imagine. So I can pass a circle around these 2 points, 2 nodes, and the circle is empty. You follow what I'm saying? If that happens, and it turns out that all the points on the convex hull, this is on the outer boundary, you can always find an empty circle. Good. Now, if by mistake you try to connect this and let me see. If by mistake you want to connect this and this, you can't. You try to draw this thing, then this will be included. You try to do this thing, this will be included. You can't. If I try to connect this one and this one, it will not be able. So let me see. Let me try to connect this one. You try to draw another circle. No matter in what way you draw the circle that passes through this thing will never be empty. So if you keep on trying this thing, so for example, here you can do it. Did you get it? Insight? What is the solution space here? We are choosing 2 things out of n things. And it's just 2. Actually, I made a mistake here. And choose, yeah, this is fine. And choose 2 will be how much? Huh?
N squared?
Yes. A magnitude of 1 is a huge improvement. So if in a straightforward way you do it, so solution space is or number of candidate triangles, would be, or candidate node pairs is equal to n choose 2 equal to, I don't write order of n square base 2 mathematical law, you can think. So if it was 10, n cube will become 1000, right? N square will become 100. It's a substantial improvement. Well, there is more than that. In 1980 or 78, Michael Samos from Yale University actually found a clever way of doing this thing, and not in n square. It is even cleverer way. Samos. Actually, it was his PhD dissertation in Yale University in 1978, I think. Order of, well, I always like that. You can take n log n. N log n is much faster than n square. Just think like that. It is not as fast as just 1 here, but it is much faster. And almost everybody use that algorithm. Actually, adaptation of that algorithm was given by a guy working in AT&T Bell Lab at that time. And the code is actually available, not the source code, but the compiled code is available. You can go and download it actually to do the triangulation, given the triangulation. And actually we use that in some of the work that Aaron and I have been doing. I actually use that one. So, when you use, I'm explaining, I have not gone to n log n. You cannot understand that one now because I need to do something else. But if you can grasp n square, that's good enough. So, I do like this. I can draw empty circle. I can draw empty circle. So, now there is a trick. Look, I can draw empty circle here because I can do this thing. It need not be diameter. Don't think that it has to be diameter. It can be any color, but the circle has to be empty. And then when these 4 points are co-circular, which is very rare to happen, then you can choose any one. Probably in this case, it will be this one. So like that you continue. And then so you got the triangles. So do you guys get, at least by hand, you can do it triangulation now, right? You take a pair, if you can pass a empty circle through that pair, continue doing like that, you get a triangulation. Okay, but this will need what kind of time? N square time. If there are n points, the time to compute that triangulation will be proportional to the square of n, which is not very slow as n cube that traditional people used to do it. It is much faster than n cube, but it is not the fastest one known. The fastest one known works in n square, it works in n log n time. So do you guys get the idea that there are 2 ways? One by, how much time we have left? Another 20 minutes, right?
Probably, or 10, maybe.
Okay, 10 minutes, okay, sorry. So one is the brute force way, another is the Delaunay triangulation, right? Now I want to issue a little bit of another thing. We do triangulation because it is easy to do and it is always, solution always exists. But recently, more and more, they are going with another structure, like hexagons or quadrilaterals. So quadrangles. It's much harder. So, actually, the need for quadrangulation actually came from fluid flow community actually. They said that in certain circumstances, the error in computation in finite element analysis converges quicker if it is a quadrangulation than triangulation. So people started working on quadrangulation. Oh, let's work in quadrangulation. There are positive results, there are negative results. No matter what, quadrangulation may not be possible always, that's the problem. So you are given a set of points, you want to partition into quadrilaterals. Well, you can have like 98% quadrilaterals, but there will be maybe 2% trapped triangles. You follow what I'm saying? I will give you an example. Suppose I take this one, very simple. Well, of course, I do like this, I do like this, I do like this, I do like this, I do like this. Well, I can't quadrangulate it, right? If the points are given like this, then I'm forced to have it a quadrilateral and a rectangle, right? So the folks in fluid flow community, I read a couple of papers, they said, since we have so much of literature in triangulation, so much of code using photon program has been already done in triangulation, why do you want to go for quadrangulation? Let's try to somehow work with the triangulation and then get to the quadrangulation. So they said, work with the existing triangulation to generate quadrangulation. There are so many other issues I cannot discuss today, but is all right, collapse adjacent triangles to make quadrilateral. This is what they do actually. So I will collapse. I'll throw it up this side. Maybe I'll throw out this one. I'll throw out this one. I'll throw this one. Maybe I'll throw this one. Oh, I have not completed this try. So yeah, I'll throw this one. And maybe I'll throw, so I will throw this one. Maybe I'll throw this one. Whoops. I have one trap triangle. Right? But which is good. So many quadrilaterals, only one trap triangle.
There's one in the center also.
Yeah. So look, I got confused. So I got like this, and then there will be two trap triangles. This is a trap. This is a trap. You know what I'm saying? And there are many. Actually, I have a couple of papers. One of my master's student wrote a thesis on generating these things. And we were thinking of applying on his code, but we just talked about it. Someday. Actually, I presented, Daryl and I presented this thing in ASME in St. Louis, right?
Mm-hmm.
Yeah, St. Louis. It was very well received actually. Lot of questions about this thing because those folks really wanted to have it. We also have a concept of what is called Hamiltonian triangulation and Hamiltonian quadrangulation, where some other time we will discuss about that. Any questions, guys? Let me not take too much time here, no, but yeah.
How much does it affect like, the calculations that you do using the mesh to have it mixed, to have triangles and
Yes.
what
If the number of quadrilaterals is substantially large compared to number of triangles, then it is very good, because look, number of quadrilaterals will be less than the number of triangles, right? So total amount of computation will be, number of states will be less, right? If there are proportionally like 30% trap triangle and 70% quadrilaterals, the equations that they show on triangles and the equations that they show on quadrilaterals are very different. So the extrapolation using quadrilateral points and extrapolation using triangle points will be different. And there is one more thing. If you are doing a refinement of the mesh, adaptive refinement, triangles are much easier. You know why? If you take a center point in the triangle, it becomes again triangle very nicely. But quadrilateral is not that easy. Do you follow what I'm saying? And there is another notion which I don't want to explain. This is what is called conformal. Conformal means you don't want to have a triangle like this or a quadrilateral like this. That's nonsense, actually. Not nonsense, but it's like sitting. One vertex, another vertex, another vertex, and people will say that is a quadrilateral, because literally speaking, this is one side, this is inside, this is one side. But actually speaking, if two sides are collinear like this line, like that, then it's like sitting, But if you are not careful and if you refine it like that, you will have a quadrilateral like that. Actually, it happens. So there are issues, So that, for example, in this case, you can choose another point here, and then you can do like this, and then I can do like this. Very nicely, if you are going to do it for quadrilaterals. Triangle has been refined into quadrilateral, right? Now the trick is where the solution gradient is changing very fast, you refine it. Where the solution gradient is not changing fast, you keep as it is. That's called adaptive mesh generation. So going back and forth between triangle and quadrilateral and adaptive mesh generation will be very appropriate. Yeah. I think I talked too much there.
Okay, any other questions for Laxmi?
Now, Daryl, you have to wrap it up with respect to.
Yeah, do you understand why we're, let me just put something for a minute.
Yeah.
Do you know why we're talking about this, about meshes?
But I don't.
When you start getting to PDEs, you're going to have, for example, I've got a slab. And maybe this side is hot, this side is cold, and maybe this is adiabatic, all right? And so I insulate the top and bottom. All right, I would like to solve for that problem. Now I know what the governing equation is. I can write that out right away. Right? So now I've got a PDE that I have to solve, and I say, oh, this is what he means by the problem domain. Right? So what we're going to do is come up with the solution, and that means creating a mesh. And so you now have to decide, well, what kind of mesh am I going to use? And every point in the mesh, the intersections of the mesh lines, is where you're obtaining your solution. That's why you had matrices in the very beginning, because you have a lot of mesh points. What do you get? An n by n matrix to solve. So you're solving that equation on each intersection. And so what Laxmi is saying, there's an optimal mesh that can be created. You pre-describe kind of what's that mesh density? How many points do I want? Do I want 10 by 10? Do I want 1,000 by 1,000? All right, now you begin to think, well, I can solve a 10 by 10, but remember why we did Taylor series? We know if I have more points, what happens to the delta x or the delta y? You want them to shrink. And Taylor series says, if I shrink to 0, I get the exact equation. But I can't do that because I'm approximating. So the trick to this is trying to come up with that best mesh and the density. Now, if I run 1,000 by 1,000, of course it'll be more accurate. I might have to come back in 2 days. Maybe I can't wait around for that. So I have to find something that's going to give me an answer that's going to be good enough. All right, and so that's what he does, is saying, all right, based on the density that you want, this is the optimum configuration. That's the name of the game. That's what's really going on. Shalene and I just came back from a conference in Chicago that actually deals with these kinds of problems. You know, for 3 days. Just all kinds of very intricate and difficult solutions and techniques that are being used to solve those kinds of things. Okay, well, thanks very much.
It is always a pleasure to work with Darrell and his book.
He always gets us in trouble. This process again, calculating the function values at 125 and 162.5, I get then a minus 0.147. What does this mean? I have a sign change. So that says, oh, I've got to go a little lower. So I go 125 plus 162.5 divided by 2, I get 143.75. All right, I'm going to check my error at this level. And it turns out the error between the exact solution, which is 142.73 and 143.75, I get something around 0.709%. So that's not too bad. All right, so I've done that in just several steps, iterations. All right, now here's what happens. This is what's really going on when we go through the process. Here's the first iteration. You guess 2 values. Right? You're going to say, well, this is what I get, x of r. So they say, well, that's not quite right. So I'll take x of r and x of u. I'll have that again. I get a new value, x of r, setting it here. All right? Likewise, then I go, oh, I might have a sign change, so maybe I'll do this value and that value. I'll have it again. And then between here and here, you see what's happening? You see the sequence as you go through the process. That's what's really going on. All right, now this is the error that's associated with the bisection method. So it's the true value versus the approximate value. And so you see the approximate error tails off like this. All right, this is what happens as far as the true error. Anybody have an idea why this is doing this? All right, it's doing jumps back and forth. And so what you're going to wind up getting is something as you approximate this, as you get closer and closer to the actual value, these sudden jumps and changes in here, these discontinuities will begin to change and narrow, get smaller. So that would be the true approximation error versus these jumps from doing the approximation that you're doing or letting the computer do.